Continuing with our discussion, okay. Pressure gauges. So there are the two types of pressure gauges that are most commonly used. One of which is open tube manometer. This is the simplest pressure gauge. The U-shaped tube contains a liquid of density ρ, often water or mercury, as shown in the figure. Okay, so the equation is given as the absolute pressure plus the gauge pressure at height 1, okay, will be equal to the atmospheric pressure, okay, plus the gauge pressure at y2. So simplifying this equation, that gives you absolute pressure minus atmospheric pressure will be equal to the difference of the two gauge pressure, or simply that is the gauge pressure. Okay, so P is denoted as absolute pressure, and the difference between P minus atmospheric pressure will be equal to the gauge pressure, rho gh. Okay. Second one is the mercury barometer. So it consists of a long glass tube as shown in the figure, okay, and closed at one end, okay, that has been filled with mercury and then inverted in a dish of mercury. Okay, atmospheric pressure can also be the absolute pressure, which is also will be equal to the gauge pressure. So buoyancy is a familiar phenomenon. So a body immersed in water seems to weigh less than weight when it is in air. So when the body is less dense than the fluid, it floats. Okay, the human body usually floats in water, and a helium-filled balloon floats in air. So Archimedes' principle. So when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So as you can see, so the weight or body, okay, as shown in figure B, will be the weight of the body will be equal to the weight of the fluid immersed. Okay, so that is buoyancy is an upward direction, okay, upward force. CG represents central gravity. Okay, so illustration 9.6. So a 15 kilogram solid gold statue is raised from the sea bottom. So what is the tension in the hoisting cable? Assume massless when the statue is at rest and completely underwater, and B, at rest and completely out of the water. So both scenario are at rest, okay, but then A is completely underwater and B is completely out of the water, or simply that is in the air. Okay, so in both cases the statue is in equilibrium and experiences three forces, that is the weight, the cable, and the buoyant force. So as you can see in the free body diagram, this will be the tension on the cable and the weight of the statue, which is equivalent to mass multiplied by acceleration due to gravity, and the buoyant force is acting upward. Okay, so the buoyant force equals the weight of this same volume of sea water. Okay, so that is the volume will be equal to mass all over density. So this is derived from the density is equivalent to mass multiplied by volume. So the volume here is what is this? Volume of seawater will be mass of statue all over density of the gold, which is mass of the statue is 15 kilograms, and the density of gold from the table is 19.3 times 10 to the third power, or this is simply 19,300 kilograms per cubic meter, and the volume of this will give us 7.77 times 10 to the negative 4 cubic meter. Okay, so the buoyant force of the seawater equals the weight of the same volume of seawater. So buoyant force will be equal to weight of the seawater, which will give us mass of seawater multiplied by acceleration due to gravity. But then mass is equivalent to density multiplied by volume. Okay, so density of the seawater multiplied by the volume multiplied by acceleration due to gravity. So therefore the buoyant force of seawater is density of seawater from the given table is given 1030 kilograms per cubic meter. So multiply by the volume, which is 7.77 times 10 to the negative 4 cubic meter multiplied by acceleration due to gravity, and the buoyant force is 7.78 newtons. Okay, so the statue is at rest, so the net external force acting on it is 0. Okay, so summation of forces along the y will be equal to 0. This is at rest or at equilibrium state. Okay, so therefore from the FBD, so tension, okay, this is for letter A, which is completely underwater. So the tension under seawater plus the buoyant force of the seawater minus its weight, negative for weight because it is in downward direction, so will be equal to 0. So the tension now, okay, solving for the tension, uh, simplifying this equation, that will give you, this will become negative mg, or weight will become positive, and that is negative. So weight minus buoyant force, so that is weight is mass multiplied by acceleration due to gravity minus 7.78 newtons. So that will give us an answer of tension of the hoisting cable when completely immersed or underwater is 37 newtons. Okay, so for letter B, okay, so the buoyant force on air of the on the statue is will be equal to what? Mass multiplied by acceleration due to gravity, or simply weight, right? So that is mass is density multiplied by volume. So density of air is 1.2 kilograms per cubic meter multiplied by the volume. Okay, and this gives us 7.77 times 10 negative 4 cubic meter multiplied by acceleration due to gravity, and the buoyant force on air is 9.1 millinewton. So this is probably this is negligible because it is very small. Okay, so the buoyant force in air is relatively small and can be neglected. So therefore summation of forces along y, okay, since the buoyant force on air is neglected, so we will not consider this anymore. So therefore the tension on air will be equal to weight of the statue. So tension of air will be simply mass multiplied by acceleration due to gravity, and this gives us a value of 147.15 newtons. So illustration 9.7, so this is a slab of ice floats on a freshwater lake. What minimum volume must the slab have for a 45-kilogram woman to be able to stand on it without getting her feet wet? Okay, so the question is, what is the minimum volume so that the woman wouldn't get her feet wet. Okay, so concept and principle for this particular problem. So when an object is partially or fully submerged in a fluid, the fluid exerts on the object an upward force called buoyant force. So according to Archimedes' principle, the magnitude of buoyant force is equal to the weight of the fluid displaced by the object, which is buoyant force is equivalent to the density of the fluid multiplied by the volume displaced, okay, uh, okay, multiplied by acceleration due to gravity. So another concept we will be using is the weight. Okay, so the weight of an object of a mass m is the magnitude of force acting on the object. So weight is equivalent to mass multiplied by acceleration due to gravity. And another concept will be the density. So the density of the material that has a mass m and a volume of v is defined as density is equivalent to mass all over volume, or simply mass is will be equal to density multiplied by volume. Okay, so the given the mass of the woman 65 kilograms, density of the ice from the table, okay, so 0.92 times 10 or 920 kilogram per cubic meter, and the density of water, okay, is 1,000 kilogram per cubic meter. Okay, so FBD, okay, so free body diagram. So let's say this is the slab, okay, a woman is standing here, so tendency the weight of the woman acts downward. Okay, also the weight of the ice where the woman stands is acting downward, and the buoyant force is acting upward. Okay, so from the FBD, so this is, let's say that this is at rest. Okay, so summation of forces along y will be equal to 0. So that is the buoyant force is positive. So buoyant force minus the weight of the woman, okay, minus weight of the ice will be equal to 0. So buoyant force, okay, from our formula, that is the density of the fluid, okay, multiplied by volume displaced, and acceleration due to gravity. So density of the water, okay, the fluid, volume displaced by the ice multiplied by acceleration due to gravity, minus weight of the woman is mass multiplied by acceleration due to gravity. So that's the mass of the woman multiplied by acceleration due to gravity, and minus weight, so mass acceleration due to gravity, that is the mass of the ice, okay, multiplied by acceleration due to gravity. Okay, then simplifying this equation, you can factor out acceleration due to gravity, right? Okay, you can divide both sides by acceleration due to gravity, so acceleration due to gravity will be eliminated on all terms. So that leads us to this equation. Okay, so density of water, volume of the ice, minus mass of the woman, minus mass of the ice. Okay, then okay, so mm, the mass of ice is not given, right? Okay, but then from this formula, okay, you can solve for mass, which is equivalent to density multiplied by volume. So that is the density of the ice, okay, multiplied by volume of the ice. That gives us the mass of the ice. Okay, now combining that those who have similar terms, which is volume of the ice, volume of the ice, then the mass of the woman will be transposed to the other side. Okay, so that gives us this one. Okay, oops, so negative becomes positive, so this is positive value. Okay, so negative mass woman transposed to the other side, so that becomes positive. So therefore density of water multiplied by volume of ice, then minus density of ice, volume of ice will be equal to, then this becomes positive. Okay, positive. Now from this equation you can factor out volume of ice, right? So that will lead us to this given equation. So volume of water minus volume of ice, and factored out volume of ice. Okay, then dividing both sides by density of water minus density of ice, so that volume of ice will be retained. Okay, so volume of ice will be equal to mass of woman all over density of water minus density of ice. So from this equation, okay, we can now substitute the numerical values of mass of the woman, density of water, okay, and the density of ice. So that gives us volume of the ice will be equal to the mass of the woman is 65 kilograms, divided by density of water is 1000 kilogram, okay, and minus density of ice, which is 920 kilograms per cubic meter. So simplifying this, you'll have a volume of the ice will be 0.8125 cubic meter. So fluid flow. An ideal fluid flow is a fluid that is incompressible. So that is, the density can change and has no internal friction called viscosity. Okay, so this will be the formula used, okay, uh, to be used in continuity equation for an incompressible fluid. Okay, so the product of the area, cross-sectional area, multiplied by velocity is the volume flow rate. Okay, so the volume flow rate, which is equal to the product of cross-sectional area, okay, multiplied by velocity. So recall this formula, okay. So we will be using this formula for continuity equation for an incompressible fluid. Okay, so let's say this example, a shower head. Okay, a shower head has 20 circular openings, each with radius 1 millimeter. So the shower head is connected to a pipe with a radius of 0.80 centimeter. So if the speed of the water in the pipe is 3 meters per second, what is the speed as it exits the shower head openings? Okay, so probably you have encountered a shower head, okay, or some of you do have this on their bathroom. Okay, so solution, so concept and principle. So this problem falls under continuity equation of for an incompressible fluid, which has a formula of uh, the volume flow rate at point 1 will be equal to the volume flow rate at point 2. Okay, where V1 and V2 are the speed of flow at 2 points, and area 1 and area 2, or A1, A2, are the cross-sectional area tube at 2 points. Okay, so given you have 20 circular openings, okay, at point, let's say at point 1, okay, radius of the openings are 1 millimeter, so they should be converted to meters. So this will give us 1 times 10 to the negative 3 meters, okay, and that is centimeters. So you divide that by 100 centimeters to give you a unit of meter. Okay, so that is will give us 0.8 times 10 to the negative 2 meter, and volume at point 2, or in the tube, okay, or the pipe with radius 0.8 centimeters, or 0.8 times 10 to the negative 2 meter, has a velocity of 3 meters per second. Now the question is, what is the speed as it exits the shower head opening? So the speed of the fluid, okay, on the openings of the shower head. Okay, now using this formula, at point 1 there are 20 circular openings, so multiply by volume flow rate at point 1 or from the opening will be equal to the volume flow rate from the pipe. So that will substitute or simplifying this equation. So we are solving for V1, okay, at point 1 or from the openings. Okay, so dividing both sides by n area 1, right? So that V1 will remain. So therefore, there's a denominator here, n a1. Okay, so the velocity, the speed at point 1 or the speed at the shower head openings will be equal to volume flow rate at the pipe divided by number of openings and the cross-sectional area of those openings. Substituting with circular openings, okay, and simply a pipe with radius. So you need the area of a circle. Okay, so that is pi r squared because the given are in radius. So pi r2 squared multiplied by v2, right? R2 is 0.8 times 10 negative 2, okay, and then divide by n, which is 20, then pi r1 squared. R1 is 1 times 10 to the negative 3 meters. So simplifying this, the speed at the openings will be 9.6 meters per second. So illustration 9.9, okay. Probably I will leave this for your activity of the day. Okay, this is one of the activity for the day. Okay, I'll just skip this problem. So Bernoulli's equation states that the work done on a unit volume of fluid by surrounding fluid is equal to the sum of the changes in kinetic and potential energies per unit volume that occur during the flow. So this is the kinetic and potential energies per unit volume. Let's say this is zero point 0.1, okay, will be equal to the uh, sum of kinetic and potential energies per unit volume at part 2. Okay, so when the fluid is not moving, okay, we'll have this formula. So but then the fluid is moving, okay, or flowing, we will use this equation. So let's say illustration 9.10, a sealed tank containing seawater to a height of 11 meters also contains air above the water at a gauge pressure of 3 atmosphere. Water flows out from the bottom through a small hole. Okay, how fast is this water moving? So solution for this problem. Okay, so the work done on a unit volume of fluid by surrounding fluid is equal to the sum of changes in kinetic and potential energies per unit volume that occur during the flow. Okay, so if there is a hole in the tank, tendency water leaks out. So there is a movement or fluid flow. So we will be using this equation. Okay, let's say from this given, okay, problem, there's a water tank which has air on top of it, okay, and this tank contains seawater, okay, and it has a height of 11 meters. Okay, let's say at point 2 here, that is the hole. Okay, let's say at any point at the bottom. Okay, so water flows out from the bottom through a small hole. Okay, so how fast is this water moving? Okay, so assume that the tank is very big. Okay, so the velocity at any point of water in the surface is almost zero. Okay, it's very slow, so water coming out from this tank is very small. Okay, tendency water movement is so slow that it's almost zero. Okay, let us assume that the tank is very big. Okay, so the pressure in a fluid with uniform density is given by absolute pressure will be equal to the atmospheric pressure plus the gauge pressure. Okay, let us now look at the given. So if we assume that the tank is very big and the velocity at that point, water coming out, let's say that is 0. Okay, and the height of the water is 11 meters. Atmospheric pressure, okay, gauge pressure at of 3 atmosphere. Let us convert that to Pascal. So 1 atmosphere will be equal to 1.013 times 10 to the 5 Pascal. So that gives us 303,900 Pascal. So height of 2 at point 2, okay, let's say that is the bottom. Okay, height is 0. Okay, so at point 2, let us consider point 2 using fluid with uniform density using this equation. Okay, so the absolute pressure will be equal to atmospheric pressure plus uh, gauge pressure. So at point 2, okay, pressure at point 2 will be equal to the atmospheric pressure plus density gauge pressure. Okay, so since atmospheric pressure is 0, okay, then gauge pressure, so this is density of seawater, then this is acceleration due to gravity, and height 2 is at the bottom, so that gives us 0. Okay, so this is also 0. So the pressure at point 2, okay, will be 0. Okay, now using Bernoulli's equation, okay, this equation to solve for velocity point 2. Okay, so using Bernoulli's equation, okay, so Bernoulli's equation is this one, so that is y1 is height 1 at point 1. Okay, pressure 1.1, then density acceleration due to gravity height 1, so that is height 1, then 1 half density velocity 1 squared. Okay, then will be equal to p2 at point 2 plus density acceleration due to gravity height at 2 point 2, then 1 half density velocity 2 squared. So we have said that pressure at point 2 is 0, height at point 2, right, is 0. Okay, so this is also 0. Then we have assumed that velocity 1 is 0, right, this becomes 0. Okay, now so simplifying that equation will lead us to uh, pressure at point 1 plus gauge pressure at height 1, okay, then will be equal to kinetic energy. Okay, right. Now simplifying this equation, solving for the velocity 2. Okay, so that is v of 2 squared, so this will 2 multiply both sides by 2, so there will be 2 here. Okay, then dividing both sides by density, so this will be the v squared. Then substituting the given values, p1 is 3 atmosphere, which is 303,900, right? Then density of the seawater, okay, of the seawater or of the fluid. Then acceleration, which is 9.81, and height is 11. Then density of seawater. Okay. Then taking square root on both sides, that will give us this equation. So that is 2 multiplied by this is pressure at point 1, 303,900 Pascal, plus uh, density 1.03 or 1030 kilograms per cubic square meter. Okay, then 9.81, then height is 11, and then 1030 again. Then simplifying this using your calculator, you'll have an answer of the velocity at the bottom or at point 2 will be 28.39 meter per second. So illustration 9.11. Okay, you can solve this problem. uh, this will be one of the another activity. Okay, I'll just leave it for you to answer. So illustration 9.2. Okay, so vertical U-tube of uniform inner cross-section contains mercury in both sides of its arms. Okay, so an ice of which density is 930 kilograms per cubic meter, a column of length 13 meters is introduced into one of its arms. Okay, now oil of density 750 kilogram per cubic meter is poured into the other left arm. Okay, until the upper surface of the oil and the ice are in the same horizontal level. So let's say they reach this after pouring. Okay, they reach of the same horizontal level. Now find the length of the oil column on the given figure. So the density of mercury is 13.6 times 10 to the 3 kilogram per cubic meter. Okay, now concept is, since ice is much denser than oil, the level of mercury in the right will be higher than that of the arm as shown in the figure. Okay, so since ice is much denser than oil, so it will the level of the mercury on the right side will be higher than on that on the left side. Okay, so the pressure at point A, let's say at point A, say here, point A, when they reach at the same level. Okay, so the atmospheric pressure plus the gauge pressure of the oil plus the gauge pressure of the mercury. Okay, so pressure at point B, let's say here at point B. So okay, so pressure at point B, atmospheric pressure by plus the gauge pressure of the ice. Okay, so the given density of ice is 930 kilograms per cubic meter. Height of the ice is 13 meters. Density of oil is 750 kilograms per cubic meter, and the density of mercury is 13,600 kilograms per cubic meter. Okay, so we are determining the length of the oil column, which is h here. Okay, height of the oil. Now since the pressure at the same horizontal level is the same, so pressure at point A and pressure at point B, okay, the same level are equal. We can say that pressure at point A will be equal to pressure at point B. So pressure at point A gives this equation, and pressure at point B gives this equation. Okay, so substituting those equations to point A and point B, this will become its equation. Now atmospheric pressure can be eliminated. Okay, and the given equation will give us now this equation. Okay, so gauge pressures of oil, mercury, and that of the ice. Okay, so So from this equation, okay, they all have acceleration due to gravity, and this can be factored out here, okay, and dividing both sides by acceleration due to gravity, okay, so dividing both sides by acceleration due to gravity, this is now our new equation. Okay, so substituting the values, so density of oil is 750 kilograms per cubic meter multiplied by height of the oil, okay, plus density of mercury, okay, multiplied by the height of the mercury, this one, height of this mercury. So height of the mercury will be 13, the total, okay, total 13 minus H, so 13 minus HO, okay, then will be equal to density of the ice, which is 930 kilograms per cubic meter multiplied by its height of 13, okay, then simplifying this equation, this becomes 713 multiply, so positive, then negative 13.6 HO, okay, then will be equal to, okay, 12,900 kilograms. Then simplifying this and combining like with like terms, so this is a constant and that is also a constant, so this becomes negative 176,800, okay, negative, so 12,900 minus 176,800 kilograms, okay, so that gives us a value of negative 163,900 kilograms per cubic, okay, square meter. Why is it square meter? So meter multiplied by so this can be eliminated, okay, this becomes square, right? Similarly, this is 13 meters multiplied by that is square, okay, correct units. Now, so dividing both sides by negative 12,850 to solve for the height of the oil. So height of the oil now will give us a positive value, which is 12.75 meters.